Governments and policymakers frame the rare earth supply chain as an extraction problem, operating on the assumption that securing domestic ore will neutralize strategic vulnerabilities. But geology is not the constraint. Rare earth ore deposits are scattered across multiple continents. The actual bottleneck lies downstream, concentrated in a highly localized network of refining facilities. Digging raw ore out of the ground generates the absolute smallest share of economic value in this entire global industry. The true center of gravity is the midstream. This is a sequence of highly complex operations, including chemical cracking, solvent extraction, and metallurgical alloying. This extreme concentration of processing capability is not an accident of market economics. It is strictly enforced by the thermodynamic limits of separation science and the severe environmental liabilities attached to the raw materials. Treating rare earths as a simple resource extraction issue ignores the physical science that actually governs the supply chain. The reliance on these specific elements originates entirely in the atomic structure of the lanthanide series, specifically a feature known as the 4F electron shell. This subatomic configuration delivers a unique combination of magnetic, optical, and catalytic behaviors. Alternative, non-rare earth materials simply lack the electron structure to replicate these physical responses. Modern industrial infrastructure relies entirely on these properties. Electric vehicle traction motors, defense aerospace systems, and petrochemical refineries require materials that behave predictably under extreme stress. Attempting to substitute rare earths out of these high-performance sectors results in severe performance degradation, massive losses in energy efficiency, and increased physical weight. The geopolitical leverage exerted through the rare earth market is a direct manifestation of quantum physics. To understand how this physics dictates industrial design, look inside an interior permanent magnet traction motor used to power modern electric vehicles. An interior permanent magnet, or IPM, motor is a design that buries magnets deep inside the rotor to maximize continuous torque. The extreme power density of these motors relies entirely on the performance of a specific material, neodymium iron boron, or NdFeB magnets. Diving into the Nd2Fe14b crystal phase reveals how this magnetic power is generated. Iron atoms provide raw magnetization, while neodymium's unpaired 4F electrons provide critical alignment. This magnetocrystalline anisotropy locks magnetic moments along a preferred axis, making the magnet permanent. But this pure crystal structure harbors a fatal vulnerability. It rapidly loses its coercivity, its resistance to becoming demagnetized, when exposed to high thermal loads. Once temperatures exceed 150 degrees Celsius, the magnetic domain walls begin to depin and slip, leading to total structural failure of the magnetic field. Because electric vehicle motors and aerospace actuators routinely operate above this exact thermal threshold, pure NdFeB is completely useless for these intense environments. Engineers solve this heat problem through an advanced metallurgical intervention called grain boundary diffusion. This process introduces specific heavy rare earth elements, typically dysprosium or terbium, into the physical structure of the magnet after it has been formed. During diffusion, dysprosium atoms migrate specifically into the narrow boundaries separating individual Nd2Fe14b crystals. They form local, high anisotropy shells around the grains. These shells act as physical anchors, tightly pinning magnetic domains and stabilizing the entire structure against intense heat. Without this highly specific heavy rare earth intervention, modern electromechanical systems would require massive, highly inefficient magnets, destroying the precise power-to-weight ratios required by modern engineering standards. But actually acquiring pure dysprosium from raw mined ore presents a massive industrial hurdle. Because all lanthanides are chemically almost identical to one another, isolating a single element using simple separation techniques is impossible. Refineries use solvent extraction, governed by distribution coefficients, how an element divides between two unmixable liquids. Passing related heavy rare earths like dysprosium and terbium through this bath yields razor-thin distribution coefficients, meaning only a microscopic percentage successfully separates in a single stage. To achieve the high purities required for magnet manufacturing, operators must force these liquids through a continuously looping train of hundreds of sequential extraction baths. This setup is exceptionally fragile. A slight deviation in pH, acidity, or impurity load will immediately collapse the separation efficiency across the entire circuit. This brutal physical chemistry restricts global capacity to a handful of operators who possess deep, tacit engineering knowledge. It structurally prevents any rapid expansion of global supply. And we have to move one step further upstream to fully understand the bottleneck. Before solvent extraction can even begin, the raw mineral concentrates must undergo chemical conversion in a phase known as cracking. Cracking requires severe industrial conditions. Facilities must bake the hard mineral concentrates in concentrated acid at temperatures exceeding 500 degrees Celsius just to create a usable leach solution. This aggressive breakdown reveals a hidden, devastating environmental cost. The cracking process unlocks naturally occurring radioactive elements that were safely trapped inside the raw ore. Specifically, the waste streams that emerge from this stage are heavily contaminated with radioactive thorium and uranium. Safely managing these radioactive residues requires strict environmental engineering, including impermeable liners, groundwater controls, and long-term seismic-resistant containment structures. The presence of these radioactive byproducts triggers intense public opposition, safety fears, and strict regulatory scrutiny. The inability to cheaply or legally manage radioactive thorium effectively bans this critical midstream step in many Western jurisdictions, forcing a total reliance on offshore processing. Once the materials survive extraction, they enter a global shipping network that is highly rigid and prone to failure. Intermediate rare earth chlorides are highly corrosive. During long maritime transit, they absorb moisture and release acidic vapors, requiring specialized, expensive containment. Refined rare earth metal powders present a different threat. They are pyrophoric, meaning they will spontaneously ignite if exposed to atmospheric oxygen, mandating precise, argon-inert packaging. But the final, most unique logistical hurdle is transporting the finished, highly powerful NdFeB magnets to the manufacturers who actually build the motors. Strict aviation regulations dictate that these finished magnets must be encased in massive steel shielding. This heavy casing ensures the intense magnetic flux doesn't interfere with the aircraft's navigation instruments. These volatile physical properties make the global logistics chain incredibly rigid, expensive to ensure, and highly vulnerable to disruption at any port or border crossing. The rare earth value chain is strictly linear and sequential. Materials must advance step by step from mine to final component. The upstream extraction processes cannot be simply bypassed, and the downstream end products cannot be substituted using current applied physical science. Ultimately, this fragile chain supports high-stakes applications that push physical materials to their absolute operational limits. A multi-billion-dollar aerospace platform relies entirely on microscopic dysprosium atoms to ensure its control surfaces remain functional under extreme aerodynamic heating. Geopolitical power in this sector stems strictly from mastering hydrometallurgical complexity and safely managing radioactive waste, not from simply possessing geological reserves. Building true supply chain resilience requires replicating that entire multi-stage midstream chemical ecosystem from scratch. Ultimately, the rare earth bottleneck remains an uncompromising engineering challenge, one that is dictated entirely by the strict laws of physics.